Hello students, welcome back to CLARI Concepts, Unleashing Conceptual Learning. For more conceptual videos on conceptual clarity, you can log into our website clariconcepts.com. Today we are going to discuss one of the very important aspects of engineering, particularly fluid mechanics. Before that, I would like to ask you one question. Let us say a fluid is flowing through this pipe, and if you are working as an engineer in some of the process industry, and if your boss comes to you and says that, hey, find out the energy contained by the fluid at this particular section. Energy contained by the fluid when fluid comes at this particular section. Now, can you quantify the energy? Think about it. Let's say he says that, okay, what happens to energy when it flows from here to here? What is the energy contained by the fluid at this particular section and at this particular section? Now, how will you quantify that in terms of joules? Rather, you can say joules per Newton or whatever it is, right? How can you give the number to that particular fluid in terms of energy? So, today in this lecture, we are going to look at the theory which really helps you to understand how you can assess, how you can estimate the energy contained by the fluid when it is flowing through a pipe at any section. Okay, so that answer can be provided by the equation called Bernoulli's equation. Okay, so let us see Bernoulli's equation, what is it and what are the terms associated with this equation. So, Bernoulli's equation can be derived from the basis of Euler's equation of motion, and if you do not know where this Euler's equation of motion came from, you look at my previous lecture where I have derived this equation. So, Euler's equation of motion says that dp by rho plus v dv plus g dz equals to 0. Now, if we integrate the entire equation, integrating the above equation, what we will get is integral dp by rho plus v dv integral plus integral g dz equals to 0. Now see, if we assume that density is constant throughout the flow, that means flow is incompressible, in that case we can take rho outside the integral sign. So this will be 1 over rho integral dp plus integral v dv plus g is anyway constant, you can take it outside, equal to 0. So now what is integral of dp will be just p by rho plus integral of v with respect to dv will be v square by 2 and integral of dz will be z just equal to 0. Now, if you divide entire equation with respect to g, what you will get, you see, on both these sides and here also g, but so 0 by g will again be 0. So, finally, you get p by rho g plus v square by 2g plus z equals to, sorry, I made a mistake. You might have said me that's mistake, right? Why? Mathematically, when you integrate, you will have some constant of proportionality, right? So, when you integrate this equation, you also will have constant. You have to add some constant, and that constant, let's say it goes on right hand side, it will become constant c, for example, right? Any constant c. C can have any values. So, this is constant basically. This is constant c. It means that if you assume the fluid to be, because this equation was derived based on the fluid assumption that fluid was steady, flow is, when we have chosen this density as constant, which means we have understood the flow is incompressible. So, this is Bernoulli's equation first of all. Let me tell you, Bernoulli's equation. Bernoulli's equation, and this is valid for first steady, then incompressible, irrotational, and fourth is inviscid. So, all these four assumptions have been taken into account. So, this equation can be valid for all these four assumptions, this kind of flow. Now, let us understand each term of this equation. So, Bernoulli equation says that it is p by rho g plus v square by 2g plus z equals to constant c, or you can say just constant. Now, what does it mean? You see, it means that let us say I have a pipe, and in a pipe a fluid is flowing, okay. Let us say fluid is flowing from section 1 to a section 2, for example. Now, if you figure out the energy content of this fluid at section 1 is, let's say, E1, and energy content of the fluid at section 2 is, let's say, E2. Now, what all will you take into account? See, the fluid will have pressure, that is P, it will have velocity, that is v, and it may also be located at the particular height, so it will also have potential energy. So normally fluid, when it is flowing through a pipe, will have three components of energy: pressure energy, kinetic energy and potential energy. So what is this P by rho g? You look at this. P by rho g reflects the pressure energy of a fluid per unit weight of fluid. That means this value is energy in pressure in terms of joules per unit weight of the fluid, is Newton. So ultimately, if you see what is P by rho g, see normally P by rho g represents P is the pressure at that particular section. So if you calculate pressure over here, let's say it is P1, P1 by rho g, if you calculate whatever number you get, that number represents the energy contained by the fluid in terms of pressure energy for per unit weight. That means 1 Newton of fluid located here has that much energy. For example, this value comes out to be 5. So 5 joules per Newton. It means that 1 Newton of fluid, when it is located over here, it has 5 joules of pressure energy. Now, what is this? This represents kinetic energy per unit weight of fluid. So V square by 2g is nothing but energy contained by the fluid in terms of kinetic energy per unit weight. That means kinetic energy contained by 1 Newton of fluid at this particular location. So let's say velocity at this location is v, and if you calculate v square by 2g, whatever number you get, that is the amount of kinetic energy obtained or retained by 1 Newton weight of fluid, right? What is z? Z is nothing but the potential energy per unit weight of fluid. That means this is also measured in joules per Newton. So Z meaning the potential energy contained by 1 Newton of fluid at this particular location. Now if you accumulate all these values together, you will get total energy contained by the fluid per unit weight. Now when you move down to another section, constant means in a same line, if there are two sections where there is in between those two sections, if there is no energy provider, no energy extractor, that means neither there is a pump, neither there is a turbine. In that case, you can say that energy at this section is equal to energy at this section, total energy of the fluid, right? So it may happen that pressure head can be turned into kinetic, kinetic into pressure, but total summation will be maintained constant. We will see some numericals on this to make you more understand about this. This is also known as pressure head. P by rho g is also known as pressure head because if you see, joules per Newton will also be equivalent to meter unit, because joules is force into displacement, Newton into meter. Newton will get cancelled, only meter will left over, right? So, and this is also known as kinetic head. Kinetic head of fluid, and this is also known as potential head. So I am giving you the alternative names because maybe in future if people talk about these heads, you may be in a position to understand what are those, right? So this is the Bernoulli's equation. We will be using this in the further examples. So let us now, so all the industries that we see, process industry, power industry, or let's say in the petrol pump, most of them you see that Bernoulli's equation plays a very significant role in defining the energy content of the fluid at any given section of the pipe where fluid is flowing, right? And it is also useful to determine what is the pressure drop, what pumping capacity is required. So we are going to see all of this one by one in the lecture. Thank you so much. See you in the next class. For more such conceptual video, you can log into our website clariconcepts.com. Thank you.